Continuing with section 8.4, we now will look at example 1b. We have the nonlinear system x squared plus y squared equals 16, x squared plus y equals 4. In this case, both of the equations are nonlinear, and our first question will be to identify the graphs of these two equations. The first equation maybe is not as familiar to you, but when you see the form x squared plus y squared equals r squared, that means that you're dealing with a circle. And if we look at this, writing it this way, the basic form is x squared plus y squared equals r squared. So this is a circle centered at the origin of radius 4. So the x squared plus y squared indicates that the circle is centered at the origin, and the 16 indicates that the radius is 4. So what we can do is, from the origin, just count out 4 units, basically plotting the x and y intercepts of the circle 4 units away from the origin, and then draw a circle as best we can through those 4 points, and that will be the graph of the first equation. So there you see my so-so attempt at a circle. Let's look at the second equation now. X squared plus y equals 4. If we solve that for y, we would have y equals minus x squared plus 4. Hopefully you recognize that to be a parabola. The vertex of the parabola is at 0, 4. It is an inverted parabola opening down and then shifted up 4 units. So the vertex would be at 0, 4, which just so happens to be one of the points that the circle passes through. So that's going to be one of the solutions of our system of equations. So let me plot some additional points for the parabola. When x is 1, y is either positive 3, y is just equal to positive 3. When x is negative 1, y is also positive 3. 2, 0, and negative 2, 0 are the x-intercepts, and 2 additional points would be 3, negative 5, and negative 3, negative 5. So now you can see the parabola passing through that collection of points that I plotted. And now, having seen the graphs of the equations in our system, we recognize that it appears there are 3 points of intersection, which I will label A, B, and C. And so our goal now is going to be to identify those points of intersection. Those are going to be solutions of our system of equations. The point A is clearly the point 0, 4. So that's the vertex of the parabola. So for B and C, it's not quite so obvious. So if we use an algebraic method, we'll be able to identify all of the points, including the ones which, graphically speaking, are not so easy to determine. So the question then would be, what algebraic method do we want to use? We could certainly use substitution to solve this system, as we did example 1a, but just for the sake of variety and to show you that the addition method can be used to solve certain systems of nonlinear equations, we'll use the addition method. What I'm going to do is rewrite the first equation just as it is, and I'm going to multiply the bottom equation by negative 1. What that will allow me to do is to add the left-hand sides and right-hand sides of the two equations in such a way that we will eliminate x from our system. When we add the equations, the x squared terms cancel. The y terms don't cancel because they are unlike terms. So what we obtain on the left-hand side would be y squared minus y. And then on the right-hand side, 16 minus 4 is 12. This gives us a quadratic equation that we can solve for y. And we can solve this rather easily by factoring. We have to first set the equation equal to 0. And then if we factor as y minus 4 times y plus 3 and set the factors to 0, we obtain y equals 4 or y equals negative 3. So it just remains now to find the corresponding x-coordinates for these two values of y. So for that purpose we can use either equation. I think I will choose to use the bottom equation, and I'm going to use a slightly different form. If I write the original form here, x squared plus y equals 4, if I solve this for x squared, I can write x squared equals 4 minus y. This will just make it easier to solve for x when we substitute the y values in. So let's just do that now. For y equals 4, we would obtain x squared equals 4 minus 4, which is 0. And it would follow from that equation that x itself would have to equal 0. What about for y equals negative 3? In that case, x squared would be 4 minus negative 3, which is 7. Taking the square roots of both sides, that would give us plus or minus the square root of 7. So it would appear that the x-coordinates corresponding to solutions B and C involve irrational numbers, the square root of 7 and negative square root of 7. Just so you are aware, the approximate value of the square root of 7 is about 2.6. So we'll see how that corresponds to our graph. Keep in mind that I did that by hand, so it may not be entirely accurate. But what we have shown is when y is 4, x is 0, that corresponds to point A, and that would be the ordered pair 0, 4. And then when y is negative 3, x is plus or minus the square root of 7. That would correspond to point B, where we would use the positive square root of 7, negative 3, and point C, where we'd use the negative square root of 7, and then again y is negative 3. So for points B and C, the y coordinate should be negative 3. You can see that for point B, it does appear that I got that right. For point C, I'm a little bit off, but that's because my circle and probably my parabola too are not graphed particularly well. And then the x coordinates should be plus or minus approximately 2.6. And again, from the graph, we're rather close to that, so it would appear within a reasonable approximation that our graph is indicating the solutions that we found algebraically. So the graph pretty closely confirms that these are the correct solutions of the system of equations. So notice with a nonlinear system you can end up with ordered pair solutions that involve irrational numbers. For our final example, example 2, we want to show both algebraically and graphically that the given nonlinear system has no solution. So what happens with a nonlinear system if there's no solution? Well, first of all, graphically speaking, there should be no points of intersection. So let's look at the graphs of these two equations. The first equation is the nonlinear equation in the pair. If I solve that for x, it's x equals y squared. Now, x equals y squared looks a lot like y equals x squared. It is a parabola. It's just that it opens, rather than opening up, it opens to the right. Its vertex is at the origin, but then it opens to the right. So y is not a function of x here. I'm going to plot some points here when x is 0, y is 0. When x is 1, y is plus or minus 1. And then 2 additional points when x is 4, y is plus or minus 2. You can determine all of these points by substituting in the appropriate values of x or of y. I'm not showing those details just to conserve some time here, but you can see that these 5 points, we can fit a parabola to these 5 points. So now you see the parabola opening to the right. So this is a parabola that opens to the right. Okay, that's our nonlinear equation in the system. The second equation is a linear equation, and that's due to the fact that x and y are both to the first power. So we could graph this by a variety of methods, but let me just solve this for y. If I subtract x from both sides, I have minus x minus 3, and if I divide by negative 3, I get y equals 1/3 x plus 1. Okay, so it's a line with slope 1/3 and y-intercept positive 1. So you'd have a y-intercept at 1, and then if you go to the right 3 and up 1, and repeat that as many times as you wish in either direction. These are the points on the line. I apologize, I made a mistake. I have a point here and a point here. There we go. So we see the line, and when we see it with a parabola, it would appear from our graph that the two graphs do not intersect. So graphically speaking, that would tell us that the system has no solution. So what if we try to solve the system algebraically? Again, there's a variety of ways we could do this. If we take the second equation, x minus 3y equals negative 3, and we replace x with y squared using this version of the first equation. So we are using substitution here. So I'm replacing the x with a y squared as shown, given from the first equation. We get a quadratic in the variable y. We can add 3 to both sides, set it equal to 0, and then we can try to solve the equation by either factoring or the quadratic formula. In this case, factoring is not going to get us anywhere, so we'd have to use the quadratic formula. The quadratic formula would give us y equals minus b plus or minus square root b squared minus 4ac over 2a. In this particular case, a is equal to 1, b is equal to negative 3, c is equal to positive 3. If I substitute those values in to the quadratic formula, I would obtain 3 plus or minus the square root of, okay, b squared would be negative 3 squared, which is 9, minus 4, a times c would be 1 times 3, which is positive 3, over 2 times a is 1, so that would just give us a 2. Okay, if I simplify this, it's 3 plus or minus the square root of 9 minus 12, which is going to give me negative 3 over 2, which gives me 3 plus or minus I square root of 3 over 2. So notice that our quadratic equation has no real solution. If you obtain a situation like this where the equation you're trying to solve has no real solution, it would indicate algebraically that the system of equations itself does not have a solution.